Good morning, good afternoon, or possibly good evening, depending on when you're watching this presentation. And thank you for attending RefComm 2020. This presentation will cover the advantages of ultrasonic flow metering in refinery applications by Panametrics. For approximately 30 minutes, this presentation will cover who is Panametrics, ultrasonic flow meters and the benefits they provide, extreme temperature metering with ultrasonic flow meters, and then application of ultrasonic flow metering in refineries, especially for extreme temperature applications. My name is Tom Michalowski, and I am a global product manager for Panametrics, a Baker Hughes company. I've been with Panametrics for over 20 years with specific experience as an application engineer, along with holding a chemical engineering degree and a master's in business administration. Unfortunately, due to time, I might not be able to answer all of the questions that you may have, so please feel free to reach out to me via my email below. For those of you who are not familiar with Panametrics, Panametrics is a leading global supplier of ultrasonic flow meters and analyzers. Our ultrasonic flow meters range from our Sentinel flow meter line for critical flow measurements for custody transfer, leak detection, and allocation, to our flare flow metering and flare optimization solutions, to our PanaFlow line of process control and safety flow meters, to our clamp-on line for a completely external flow measurement. Our analyzers start with our moisture analyzers, or hygrometers, which include multiple technologies such as aluminum oxide, TDLAS, relative humidity sensors, and chilled mirrors. These analyzers also come with our standard or custom designed sampling systems designed for proper conditioning of the fluid for the sensors. Our oxygen and gas analyzers include using galvanic fuel cells, thermal paramagnetic, and thermal conductivity technologies. Moisture, oxygen, and hydrogen measurements are critical parameters in the refinery for optimal performance, but unfortunately we will not discuss in detail during this presentation. Panametrics has a long history of ultrasonic flow monitoring and gas measurement starting here in the United States. Panametrics was founded in 1960. Without going through each bullet, some key highlights from the ultrasonic flow meters include, first, Panametrics launching its first transit time flow meter in 1979 for both liquid and gas measurement. Panametrics launched its first flare gas flow meter in 1984. Panametrics launched its first flare gas microprocessor-based flow meter in 1990. Panametrics launched its first portable clamp-on transit time flow meter in 1993. In 1995, the bundle wave technology, or BWT, was introduced for high temperature and high pressure applications. In 1999, Panametrics introduced its first steam ultrasonic flow meter. And since 1999, Panametrics has continued to innovate and engineer new ultrasonic flow meters based on the extensive installation, field experience, and technology improvements. Today, Panametrics has the widest supply of ultrasonic flow meters to meet any of your specific application needs. Our Sentinel line of ultrasonic flow meters for custody transfer, allocation, or leak detection provide the highest accuracy for your oil or hydrocarbon liquid fluids, or even your challenging cryogenic LNG measurements. Our Panametrics process meter line provides reliable, maintenance-free operation and safety-critical measurements for your liquid and gas flow measurement needs. Our clamp-on metering line provides cost-effective and completely external flow measurements for either your permanent or spot sampling requirements. Finally, our flare solutions cover your complete flare monitoring needs through our world-renowned flare flow meters, our Flare IQ advanced flare control software for flare optimization, and complete flow services for regulatory evaluations, preventative maintenance, and in-person training. Before going too far into the advantages and value that ultrasonic flow metering brings to your process unit, we should quickly review the basics of ultrasonic flow measurement. Sound waves are vibration energy that travel through gas, liquid, or solids. Sounds can be classified as either subsonic, audio, or ultrasonic. Ultrasonic are sound waves above 20,000 Hz. Ultrasound is used every day in nature and in industry. Ultrasound is used for object detection with bats and dolphins, to imaging at hospitals, to non-destructive examination of materials, for chemical cleaning, and then finally to flow measurement. Sound waves rely on a process or medium to move from one point to another. In each of these states, the sound wave has to jump from molecule to molecule. The closer together the molecules are, the quicker and better the sound wave can be transmitted across the medium. For gas processes, these molecules are spread far apart. As we look at liquid processes, the molecules are closer together, allowing for more signal to easily traverse from one side to the other. At the other end of the spectrum, we can see solids with their molecules packed tightly together, allowing for the best transmission of sound waves. We should mention that each of these states of matter fully depends on the specific molecule structures, temperatures, and pressures. This is why a gas process with hydrogen does not typically allow as strong of a signal to be transmitted through when compared to a similar volume of air, as an example. It is important to note that there are three distinct ways to lose signals. In ultrasonics, these three methods are collectively referred to as attenuation. The first one, dissipation, occurs as the ultrasonic wave propagates through a medium. Like the ripples when a pebble falls into a still pond, the farther the wave travels from the initial source, the weaker they become until they are not distinguishable from the rest of the water. Reflection occurs when a sound wave bounces off an object. In ultrasonic flow measurement, we can actually bounce a signal off of the outside of the pipe to get a measurement. However, in second phase materials, such as gaseous bubbles in a liquid stream, can cause some signals to bounce away in a different direction than what is expected. Last, absorption occurs when a sound wave is absorbed by the material until it is reduced or lost. Some materials like this might have a rough or even porous surface. In ultrasonic flow, this can be observed with process buildup, corrosion, or even some attenuative gases such as carbon dioxide. Each ultrasonic flow meter is designed to overcome attenuation by the installation method, transducer selection, signal processing, and design experience by a Panametrics application engineer. The piezoelectric effect is the ability of certain materials to generate an electrical charge in response to an implied mechanical stress. Panametrics ultrasonic transducers use this phenomena for signal creation and reception to generate and detect ultrasonic sound waves. The crystal generates sound waves when a voltage is applied to the materials. The sound wave is created when the crystal deflects in response to the applied voltage. The crystal detects sound waves when the crystal deflects as the wave strikes the sensor. This deflection creates a voltage. The signals are sent and received into the process medium to detect the flow measurement as shown by the animation. There are three main methods of ultrasonic flow measurement. Transit time is the most common method of measuring flow with an ultrasonic flow meter. I will not be discussing Doppler or correlation tagging principles. With a transit time flow meter, two transducers are mounted on opposite sides at an angle so that one transducer is upstream of the flow and the other transducer is downstream of the flow. The transducers act as a pair and both transmit and receive ultrasonic signals. However, when there is flow in the pipe, the signal from the downstream transducer will slow down as it goes against the process fluid to the upstream transducer. The opposite occurs as the signal from the upstream transducer will speed up going through the process fluid to the downstream transducer. This time difference is proportional to velocity. By knowing the pipe dimensions, a volumetric flow measurement is determined, and mass flow measurement is determined when the density of the fluid is known. With the transit time ultrasonic flow meter, the final meter can either be inline or wetted, or external or clamped on. With an inline meter, the transducer or transducer system is touching the process fluid. I use the term transducer system here since sometimes the actual transducer itself does not touch the process, but uses a buffer or other material that separates the transducer from the process. The transducer simply transmits the signal through this buffer into the process fluid. With an inline meter, the system is typically provided with a meter body or spool piece, and they are typically more accurate than an external or clamp-on meter. With an external or clamp-on system, the transducers are installed on the outside of the pipe as shown on the picture on the right. Clamp-on meters are advantageous since they can be installed on the existing pipe without stopping your process. Clamp-on meters can also be used for troubleshooting with a portable battery-powered meter. Clamp-on meters are typically less expensive than inline meters since the meter body or spool piece is not required, especially for larger size pipes. Many people now choose ultrasonic flow meters due to their natural advantages. A common choice for selecting an ultrasonic flow meter is that these types of flow meters do not drift or require periodic maintenance. Ultrasonic flow meters have no moving parts or parts that could wear over time. Therefore, an ultrasonic flow meter is very repeatable over the life of the product for excellent process control optimization and efficiency. Also, no calibration or periodic maintenance is required once installed. Calibration and maintenance translates into both extra cost and extra time to maintain the meter. Also, with ultrasonic flow meters, the sensors do not cause a pressure drop and do not waste energy. Ultrasonic meters also do not have a restriction in the pipe requiring filters or strainers. Contamination within the fluid and pipe could damage other flow meter technologies, causing drifting measurements, periodic calibration, or worst case, replacement of the meters. Ultrasonic flow meters are bidirectional, which can save you money if your process flows in both directions, such as a loading and unloading type application. Ultrasonic flow measurement is independent of temperature, pressure, viscosity, and conductivity. Therefore, an ultrasonic flow meter can be designed for different fluids and process conditions without significant impact to the measurement and process control. Ultrasonic flow meters are being selected more and more due to the increased demand for reliable flow measurements. Ultrasonic flow meters are uniquely positioned for greater accuracy and performance with no maintenance. Users have many options for internal allocation meters, pipeline monitoring, process measurements within their unit operations, blending, and other such applications. However, more and more users are continuing to transition over to ultrasonic flow meters due to the overall turn down range or ratio, no maintenance, no pressure drop, and advanced diagnostics. For extreme temperature monitoring, many users are not aware that ultrasonic flow meters are an option. Panametrics have been monitoring extreme temperature applications since the 1990s for such difficult applications. PanaFlow HT is our solution for extreme temperature application. It provides flow measurements for either process control or safety critical applications. PanaFlow HT was the world's first ultrasonic flow meter to be SIL certified. The PanaFlow HT improved on our current design with bundled wave technology to provide a better overall flow measurement based on the Panametrics heritage. This meter is also supported by the global Baker Hughes and Panametrics service and support team. PanaFlow HT utilizes our bundled wave technology. The concern with extreme temperature applications is that the transducer will be damaged by the thermal shock with the risk of cracking the crystal and permanently damaging the transducer. To resolve this issue, the transducers are located away from the extreme temperature with a bundled wave buffer. The bundled wave buffer provides a waveguide for the ultrasonic signal and produces a significantly better signal shape than a solid buffer. With this waveguide, we can go up to 600 degrees Celsius or over 1100 degrees Fahrenheit for almost measuring any application in a refinery. Also, with the BWT technology, the transducers can be accessed at any time for any reason without process shutdown and at a safe nominal temperature. This same technology can be leveraged for both liquid and gas flow measurements. PanaFlow HT is used for both process and safety control systems. With SIL certification, we achieve this certification by design. With the PanaFlow HT, we achieve a SIL 2 certification level with a single system and SIL 3 with a redundant design system as shown on the right. However, the PanaFlow HT system, we have multiple configurations of 1, 2, 3, 4, or more based on the file requirements and voting system at the measurement point. Here's a picture of a 4-path system on the bottom in which 1 point of measurement goes to the process control system and 3 measurements are going back to the safety system. Besides the PanaFlow HT, we also have our CET clamp-on transducers for extreme temperature operation. This video illustrates the high temperature of the application and how the CET transducers operate. With the CET waveguide, the transducers are kept at an ambient temperature, isolating them from the process. Our CET transducers have been used to validate flow measurements in multiple locations in which either no flow measurement existed or in which the current flow measurement required scrutiny. With the understanding of how ultrasonic flow meters function and details on extreme temperature ultrasonic flow measurement, let's move on to some examples of how ultrasonic flow meters are used in refinery applications. Ultrasonic flow meters operate everywhere in refineries, from main feed lines in and out of a refinery, to exhaust flare lines which are required for balance of plant and emissions monitoring, to the utilities measurements which you might naturally think of, and then everything in between. For the main feed lines in and out of the refinery, ultrasonic flow meters are selected for inlet crudes with high accuracy 4 or 8 path flow meters such as our Sentinel LCT4 and LCT8 with viscosity independence, and our Panaflow Z3 or Sentinel LCT4 for blending applications for final product optimization. For flare lines, ultrasonic flow meters such as our GF868 and XGF868I ultrasonic flow meters are almost exclusively used for the main refinery flares, local unit flares, and flare laterals due to the versatility they provide for monitoring extreme low flow rates and then extreme high flow rates above 300 feet per second in upset conditions. Along with extreme flow rates, the ultrasonic flow meter handles changing stream compositions, including high levels of carbon dioxide or even hydrogen. Utility measurements, including steam, nitrogen, compressed air, and water, use ultrasonic flow meters. The measurements include both low flow, low pressure steam up to high pressure, high flow steam applications with transducers such as our BWT, to plant nitrogen and air with both wetted and clamp-on system, to water measurements for large cooling pipe waters as an example. However, we will focus and review the measurements in between in specific process units such as delayed coker, the crude and vacuum distillation units, the FCCU, and the sulfur recovery units. If you are attending RefComm, you are most likely very familiar with the delayed coker unit. However, for those of you who may be new, the delayed coker is the process unit at the bottom of the refinery. Coking is the thermal cracking process designed to heat the vacuum residual oil to its thermal cracking temperature. The high temperature breaks the long chain or heavy hydrocarbon into smaller chain molecules such as gasoline oil that is more valuable and can be reused within the refinery or into petroleum coke. The basic diagram on the right-hand side shows the distillation column outlet feeding into the coker furnace with the outlet going to either one of two drums. The final coker design will depend upon the refinery throughput and could include more than one heater and more than two drums. For ultrasonic flow measurements, the numeric bubbles show the types of meters that are selected based on the fluid. For water, we typically use our Panaflow LC liquid clamp-on flow meter for hazardous areas. For lighter oils such as naphtha and LCGO, we use either our Panaflow Z3 or LZ process-wetted ultrasonic flow meter. For the flare lines, we use our XGF868I flare meter. For the fuel gas, we would use our Panaflow Z2G process gas meter. For the steam lines, we would use our XGS868I ultrasonic flow meter. However, the measurement that this slide focuses on is the heavy oil feed line into the furnace. With this measurement, the illustration on the bottom shows one example of a 2 out of 3 voting system for the safety system and one for the process control system. For this measurement, due to the high temperature and safety requirements, we provide our Panaflow HT system. In this picture, you can see an example of our Panaflow HT ultrasonic flow meter for the specific installation. The main problems with furnace feed line measurements are both reliable and safe flow measurements. Typically, non-ultrasonic flow measurement technologies have been used for these applications. The main issues for these measurements have been clogging. If these lines get clogged, they either stop feeding to the furnace and need to be shut down, or worse, have to be pigged. The absolute worst case is that the plugging in extreme conditions cause the pipe to burst, which is obviously a safety issue. Beyond clogging, recalibration, maintenance, and cleaning were common due to inconsistent measurements between the multiple flow measurements due to the clogging impulse lines and blocked membranes. Therefore, technicians were continually required for servicing these meters, which led to lack of trust in the measurements. Along with the maintenance, there was always concern about safety, with purging existing meters and exposure to technicians in these situations. The solution to these applications is our Panaflow HT ultrasonic flow meter. The Panaflow HT ultrasonic flow meter does not cause a pressure drop or any flow obstruction since the buffers do not insert into the process. Therefore, the flow is not obstructed and continues down the line like the rest of the piping. The meter does not wear or tear or drift. The Panaflow HT is purely sending the ultrasonic signal back and forth through the process fluid, and the sensing element does not have any associated drift. The transducers are accessible at nominal temperatures and can be replaced under process conditions if required, which is safe for the technician. The meters have SIL 2 or SIL 3 certification, along with all lambda values and probability of failure on demand numbers for true understanding of the meter's reliability. With the ultrasonic flow meters, they provide an understanding of the health of the measurement and stability of the process with diagnostics such as SNR, or signal to noise, and fluid sound speed. Last, ultrasonic meters are designed for safety with multiple configurations as the one shown on the last page, and materials such as stainless steel, non-chromoly, or others upon request. On the right is one of many Panametrics applications notes. Please feel free to reach out to us for a copy of the specific application note on delayed coking measurement or any other specific application note for refineries. To understand the implications of a poor measurement, let's review some scenarios which were validated with one refinery. So let's assume there are 8 heater pass lines into one furnace. Each of the passes have 24 flow measurements, 2 for the safety system and 1 for the process control. If other technology devices are used, let's assume 48 impulse lines. Finally, we'll assume 40,000 barrels per day operation capacity for the delayed coking unit with a $14 profit per barrel. With using poor quality devices, you could see operating expenses of $400,000 to $900,000 per year. With the Panaflow HT, it is zero. To understand the operating cost, it could be either the routine maintenance, purging, or an unplanned shutdown. For maintenance, this work would include calibration of the sensor and sometimes having to replace the sensing element. Assuming 24 hours per year per maintenance point, based on 24 hours times 24 meters times a labor rate of $75 per hour leads to $43,000 per year. Purging is required on the lines for a non-ultrasonic flow meter. For a 1.5 barrels per day purge rate with 48 impulse line equates to 72 barrels per day. 72 barrels per day is 26,000 barrels per year. With 26,000 barrels per year and a $14 loss profit per barrel, it equates to $364,000 per year. Last is the unplanned shutdown to flow measurements not agreeing with each other, or loss of measurement due to a clogged impulse line or membrane. With $14 profit per barrel and 40,000 barrels per day capacity, it leads to $560,000 in lost profit each day a delayed coker unit is shut down. Therefore, a reliable ultrasonic flow meter just makes sense in the long-term operation of a delayed coker unit. The crude and vacuum distillation units also utilize ultrasonic flow meters. The crude distillation unit separates the incoming crude oil into various fractions by boiling points. The vacuum distillation unit is the bottom heavy oils and residues that do not distill from the CDU. For ultrasonic flow meters, the numeric bubbles show the types that are used based on the fluid. Similar to the delayed coking unit, for water, we typically use our Panaflow LC liquid clamp-on ultrasonic flow meter for hazardous areas. For light oils such as naphtha and LCGO, we used either our Panaflow Z3 or LZ process-wetted ultrasonic flow meter. For the flare lines, we use our XGF 868i meter. For fuel gas, we would use our Panaflow Z2G process gas meter. For the steam line, we would use our XGS 868i ultrasonic flow meter for steam. Panaflow HT meters have been used especially for the crude distillation outlets or vacuum distillation inlets and at the vacuum distillation heavy bottom outlet. The fluid catalytic cracker unit is another process unit designed to crack or break the longer chain hydrocarbon fluids into more valuable products. Similar to the delayed coking unit and the main distillation units, we have a wide selection and variety of ultrasonic flow meters tailored for each measurement point. Panaflow HT meters have been used especially for the slurry oil and feedstock due to the high temperature and critical nature of these measurements. On the bottom here is a picture of one of these meters installed at the FCCU. For solvent de-asphalting, we have used this specific flow meter design at the feed of the extractor. With this measurement, you can see the high viscosity of 1800 centipoise. Due to the critical nature of the measurement, it was two-path with two separate electronic measurements for this difficult asphaltene line. Employing our BWT technology here, the flow measurement successfully replaced another flow meter measurement technology, which continued to have inconsistencies. In the sulfur recovery unit, liquid sulfur must be maintained at a constant temperature between 260 degrees Fahrenheit and 300 in order to not solidify or clog. Other flow measurement techniques have their own challenges with pressure drop and flow obstructions. If the line solidifies, it becomes extraordinarily difficult to clean up and may need a long isolation period, and a lot of safety precautions must be taken due to the presence of hydrogen sulfide. Ultrasonics have proven to work reliably in these applications using a pipe-on-pipe concept with steam heating. The picture on the right shows two examples of such systems with proven reliability for uptime, which is a common theme from a Panametrics ultrasonic flow meter. Why Panametrics? 3 reasons: knowledge, products, and experience. We have some of the original ultrasonic flow meter patents, and we have maintained our strong domain expertise. We are on our 4th and sometimes even 5th generation of ultrasonic transducers and transmitters. We're always improving on our solutions. We have experience and have seen so many different types of application and installations over the years. Just ask, and we're always willing to help. In closing, we would like to show you one additional video on how Panametric ultrasonic flow meters have provided value.
This is a major petrochemical company. They make lubricating oil. As their demands increase, it's important for them to make sure their plant runs as efficiently as possible. And that requires reliable process flow measurement. This company happened to be using older technology for batching and blending. It was pretty inefficient, and so their engineers were faced with increased maintenance expenses and significant downtime due to wear and tear, which created a pretty big impact on production throughput and was a big risk for revenue loss. That's when they got together with Baker Hughes and were recommended Panaflow ultrasonic liquid flow meters. The engineers knew these ultrasonic flow meters would save them time and money in the long run on things like maintenance and calibration. They also knew that ultrasonic flow meters work independently of temperature, pressure, conductivity, and viscosity, which was especially helpful for these guys. The previous flow meter couldn't handle the viscous product, causing a pressure loss that reduced pump efficiency. With no moving parts, no restriction in the pipe, and a full-bore flow cell design, the Panaflow meters eliminate pressure loss, drift, and any degradation of flow. They also reduce the plant's energy usage by improving pump efficiency. The multiple-path transducer design gives them better accuracy than their old flow meter, which they need for their blending application. And if that isn't enough, the engineers can remove the ultrasonic transducers from the Panaflow meters for service or replacement without the need to shut down their process, which means less downtime, lower operational costs, and lots of money saved. It also means a happy customer.
Thank you for watching this presentation from Panametrics on ultrasonic flow metering. If you have any further questions, please feel free to reach out to us.